Welcome to a lesson on the divergence of a vector field. The goals of the video are to define the divergence of a vector field and also to determine the divergence of a vector field and interpret the results. The divergence of a vector field, as expressed here, is equal to the dot product of the partial derivative operator and the vector field f, which will give us the partial derivative of f with respect to x plus the partial derivative of g with respect to y plus the partial derivative of h with respect to z. And if f is in R2 or a two-dimensional vector field, then we'd have the partial of f with respect to x plus the partial derivative of g with respect to y. Let's talk about the meaning of the divergence of a vector field. The divergence of a vector field measures the rate of change inward or outward of a vector field, also called sinc. For a velocity vector field, this would represent the rate of flow inward or outward from a given point. If the divergence is positive, the rate of change is outward, like a heated gas that is expanding. If the divergence is negative, the rate of change is inward, like a cooled gas that is being compressed. And if the divergence is zero, the change is not inward or outward. The vector field is called incompressible. Let's take a look at an illustration of divergence. What's going to happen here is there's a little red box that's going to take the path along these blue lines. And since the divergence here is equal to 1, or it's positive, the volume of this box is going to expand or increase along this path through the vector field. Let's take a look. You can see as it takes the path, the volume of the red box is expanding. This is what it means to have a positive divergence. In this example, the divergence is negative, so as this red box takes the path of these blue lines through the vector field, the volume of this box will decrease. Now sometimes when the volume decreases, it's hard to tell because the shape of the box will change, but the net result of the volume as it passes through the vector field is decreasing. If we take a look at the red box now, notice that it's very flat and the volume of the red box has decreased as it passed through this vector field. The third possibility is when the divergence of a vector field is equal to 0, as we see here. So as the red box passes through this vector field, the volume will not change even though the shape of the box may change. So as it passes through this vector field, the volume of that red box is staying constant even though the shape of it is changing slightly. This is an example of when the divergence is equal to 0. Now let's go and take a look at our own example. Here we want to determine the divergence of the given vector field and then at the point 1, 1, 2. Let's go ahead and list the components of our vector field. So little f is going to be xy squared. G is equal to 2xz, and h is equal to 4 minus z squared y. So to determine the divergence of f, we're going to determine the partial derivative of f with respect to x, that's going to be y squared, plus the partial derivative of g with respect to y, well x and z would be constant, so that'll be 0, plus the partial derivative of h with respect to z, that's going to give us negative 2zy. Let's go ahead and simplify this. We have y squared minus 2zy. Let's go ahead and evaluate this at the point 1, 1, 2. So y is equal to 1, so we'll have 1 squared minus 2 times z, that's 2, and y is 1. So we have 1 minus 4, that's negative 3. So at this point in the vector field, the divergence is negative and therefore the rate of change would be inward at that point. Or if we had a balloon or a box at that point, the volume would be compressed. I hope you found this video helpful.